we finished roughly up to that, and then we looked at the different coefficients that the test will provide. That's where we stopped yesterday. Too loud. Okay, hopefully that works. So, one of the things about testing is that you get, depending on the variables that you use on the test, you get different answers. Okay? So you have the concrete sample here, or you have the concrete sample on the site. So quite often it's a design like that we use. We put the salt solution here, and we look at the chloride concentration in different depths. And each of that will provide you with a diffusion coefficient. So if you use this method, or you collect the dust from the site and then analyze it, you get what's called a D apparent, or D non-steady state. If you use a pure diffusion cell with no voltage flow, then you get an effective diffusion coefficient. If you use other means, rapid chloride or any other means, you get a different value. Do you think all of these are connected? Yes and no. I would say no. There's a reason for saying that. When we looked at the test yesterday, the sorptivity test, I did say you need to look at the observation very carefully. Only the observation can tell you if you're measuring the same entity. That's less noisy. Good. So it depends on the observation, okay? So I'll explain how the different mechanisms work, especially those two things called steady state and non-steady state. Have you come across this wording before? Steady state and non-steady state? Okay. In where? Yeah. Okay. It's very similar. So if you assume a small cube of concrete, okay, it's at the micro level, very, very small level. Let's say this is 1 micrometer. Okay. So for a cube like that, in one phase you have the chlorides coming in. Okay. So this phase may be closer to the surface. So this is the concrete, and that's the chloride surface, and that's where the water is, or more concrete. So clearly the flow is from the surface towards where there's no concentration. So this face of that tiny cube from within has quite a bit of chlorides coming in. The movement of chlorides or any other ion in concrete is a two-part equation. One is the transport, which is simply driven by the concentration gradient. And the second part is the reaction that it provides. Concrete is not an inert material, it's an active material. So it will react. So there are 5, let's say there are 5 chloride ions going here. 1, 2, 3, 4, 5. Depending on what's in the concrete, there may only be 4 of them that can go out. Okay? If you're using PFA or any other substitute that has more aluminate phase in it, there may only be 3 of them going out. It's not the exact chlorides that come in goes out. So 5 of them comes in, and the chlorides that were available in the system, 3 of them will have to move out to make space for more. Okay. So that difference is what we refer to as binding. Okay. Do you think this system will happen forever, or does it have a shelf life? After a certain time, the reaction potential will dry, which means the amount of chlorides it can hold back will be 0. So at that stage, if 5 comes in, there will be 5 going out. That is called a steady state flow. It's very similar to the pipe systems or hydraulic system. The flow at every section of the pipe is steady. You can quantify it. This scenario where 5 comes in, 3 or 4 goes out, is called non-steady. Okay? Where the flow is not steady, the reaction phase is dominant. This test, which you measure from the site, gives you a non-steady flow because the reaction phase is also happening. Because you're taking concrete samples at random. You have no idea whether that's in a steady state or not. So you're taking concrete sample by drilling into it. And when you plot it, what you're going to get is a non-steady flow. You're going to get a representation of the non-steady flow. Some part of it will be in steady. Other part of it will be in non-steady. There's no way we can tell it which one is in steady or not. That's why quite often people use a wording called apparent. It's apparent. Anywhere you see a word apparent means they're not sure. It's something closer to it. Okay? If you use a very similar system like that, and you put the concrete sample in the middle, and if I monitor the chloride concentration, so the chloride concentration here at the start is 0, so this is NaCl, 0.55 mole, let's say. So I'm observing the chloride concentration in this cell. Okay? So the chloride concentration, it'll be parts per million. So that's in the axis. So when time is 0, what will be the chloride concentration in here? It'll be 0, right? Hopefully, if you're not using tap water, then it'll be 0. If you're using tap water, it'll be small, like maybe 10 or 18 ppm. But with time, you're going to get a small increase. Because some of these sections are now starting to throw chlorides out, but it's not steady, it's very random. Random but quantified random, okay? And at a later stage, what will happen is the steady will pick up into a transition zone where there's more 5 coming out, 4 is coming out at that stage. And a bit later, it will become steady, okay? So if you accelerate the test by temperature or by higher concentration, you're talking about these. For a 50 mil thick sample, okay? Now, that value will change if you're using high performance concrete. This 180 could become 1 year, 2 years, 3 years. If you're using a weaker concrete, this might become much smaller, shorter. But the problem that we have for testing community is that we simply can't afford to wait till 90 days for measuring steady state. Steady state is a perfect measure. I'll explain that. So quite often we want to take measurements as close to 0 as possible so that we don't waste a lot of time. Time is money, clearly. And that's why we use the drilling method. We drill into the concrete and we collect the dust and we analyze information in this non-steady region. Okay? And this is the steady region. And there's also one more region, which is the attenuation stage. Attenuation is when the flow goes down again. Okay? All I wanted to say here was depending on where the test is measuring, you get different value. And you won't be able to correlate them directly. You can correlate them indirectly. If you quantify the reaction phase of it and add it to the value that you get here, I don't mean simply add it, then you'll be able to get the coefficient which you're getting here. And there's a lot of work has happened in that area. So we now know that I can relate this and this together using quite a nice equation. but it needs a few values like porosity and binding capacity. Okay? All I wanted to highlight was just be aware of it, because depending on where you test and what observation you're expecting, your values will be different. Therefore, if you're to classify that certain concrete as good or bad, you need to know what that classification is from. Generally speaking, the values that you get here from standardized testing will be higher, of the order nearly 5 to 8 times higher than what you get here. Okay. That's simply to the fact that if during steady state, the flow will be much higher, but by then all the pores are restricted. So although it's a higher flow, when I can say 5 comes in, 5 goes out, 5 cannot really come in, only 3 can come in and 3 can go out. Okay, because reaction will shorten all the pores into smaller units. So the values that you get here will be much smaller than the values here. If you are to do any of these testing or commercially offer any of these testing, my recommendation will be to use something called Nordic test. Okay. Nordic tests take a coding called NT build. Okay. And the number after that represents what test you're going to do. So the test that measures in this region without acceleration, without voltage acceleration, is NT build 443. Okay. The advantage of Nordic tests is that it's freely, you can download, it's free standards. Okay. If you want to go faster, there's another test called 492, which still measures in this region, but it's a migration based test, so it's a faster test. Okay. There is another one, I can't remember, I think 392. So if you Google it, you'll figure out. So NT build 392 measures in this stage. Okay. It's a very long, elaborated test. But along with that standards, there's also standards for how to drill into concrete and how to analyze chlorides using different chemical analysis. So all of those standards are free. So if you are using or referring something, use that. Some of the projects we have done in Europe for what's classified as performance-based tests, they're recommending to use 492. 492 is very similar to this test. You have a voltage being applied, and so it's very fast. Because it relies on non-steady state, you can finish it in anything between 24 to 48 hours. Sorry, 24 to 96 hours. But most of the time it's 24 hours. It's a very quick test. It was developed in Sweden. Happy enough? Any questions? Okay. There is a European standard which also relies on non-steady. But it's very similar to putting a concrete disc into salt water and taking it out after 90 days and analyzing them layer by layer. Still measures in this region. It still gives you a diffusion coefficient. It will be a non-steady diffusion coefficient, and it will give you a value in this range. Okay, it's not accelerated, so it's salt water at 0.55 moles, so you have to wait 90 days to get some form of depth. Trick of the trade is, if you're doing testing for others, take 4 cores. If you're doing the European standard test or this test, take 4 cores, open one after 35 days, split open, spray with silver nitrate. You will see the depth. That'll help you to decide how and when to drill. Okay. Sometime when you open it after 35 days, you see that nothing has happened. So you really don't need to open the rest of them. Okay. So always prescribe 4 cores. 1 for silver nitrate spray. So silver nitrate spray is a good thing for site work as well. you can take a core or you can drill a hole into site for collection, then you can spray silver nitrate afterwards to see how far the chlorides have gone in. Silver nitrate is a very fast oxidizing chemical. Be very careful when you're using your hand with it. It's the same stuff that you have it in henna. You know, the drawings that you guys make. So it's most of the commercial ones that you buy, which is not really henna, actually has silver nitrate in it. It gives you an etching on the hand. The advantage of silver nitrate is it'll react with silver readily and convert into silver chloride, which is white precipitates. That's what you can see. So have a bottle of silver nitrate with you. It shouldn't see sunlight, needless to say. So take a darker bottle. Okay, what else do you need to know? Anything else do you need to know? How do you know what you need to know? Go ahead, sorry, Sharon.
Sir, some people have referred for the same strength concrete, M40 and M40, and two authors are referring like chloride concentration have migrated for 90 days. It has migrated till half of the depth. If it is 10 cm cube, then 5 cm it has went away. And some other are saying for 90 days there was no penetration. The strength was same.
Yeah.
Even the slump values were almost similar. So, whom we should consider? Whether the 90 days for M40 is done, whether it is penetrating, and some people are saying it is not penetrating. Same for concentration 3.5%.
Okay.
So tests are same. They have drilled it and they are saying that it has not penetrated.
They both are right.
Then how should we judge that our concrete is?
You should judge based on the performance. They did say the penetration is low on the second M40, and that's suitable. No matter how you look at it, that's suitable. I'll give you an example. Pervious concrete. You're familiar with pervious concrete, yeah? How strong can a pervious concrete be? What's the maximum that you can go with the pervious concrete? I have no idea. I'm just getting your answer because that helps me to answer the next question. 40, M40? Yeah, M40 is possible. So pervious concrete against a traditional concrete, which is M40, which one will allow more chlorides? Pervious concrete. It's just going to let the flow through. They both have the same strength. One have perfect flow, nearly streamlined flow, and the other one won't flow that easily, right? Strength cannot be used as a performance indicator for durability. For the same fact, remember the pervious and the non-pervious concrete. They can be the same strength, but the flow will be completely different. Answer lies in what is in the cement matrix that they used to get that M40. If they use slow reacting, high replacement material to get that M40, I don't even know if M40 is a 28-day strength or 56-day strength. Even that might change the story. So if they use a high volume replacement concrete to get to the M40, then highly likely that concrete will perform better. Highly likely. So bottom line, you cannot use strength as a performance criteria for durability. Strength is a performance criteria for structural properties. And what we're saying is you need another performance criteria for durability based on your exposure. Okay? Chlorides are not the performance criteria if your exposure is carbonates or sulfates. You need a related exposure criteria. And this is why I was keen to tell you how to design a test. Your exposure criteria is what you should develop as a test. If your exposure is in a combined sulfate and chloride environment, that is your performance test. So you take a pond of water with sulfates and chlorides, put your concrete, see what happens, and you will see the magic of disintegrating concrete. Because sulfates will do the damage, chlorides will go faster, it'll do more damage, so it'll be very fast cycle. And that should be the performance test. I mean, in nowhere it says what should be the performance test. It's only coming to the forte in the next 5 years. European Union might say this is the performance test for chlorides. Okay, but we're nowhere near it. ultimately you as the consultant will have to define what is your performance requirement. Any questions?
So, what is the difference between chloride threshold
Okay.
and the chloride binding capacity?
Okay. So let's go back to the model here. So assume you had a steel reinforcement here. Okay. So chloride binding refers to the reaction phase in this cube. Okay. So if 5 comes in and 3 goes out, the binding capacity is, in a very simplistic term, the binding capacity is 2. Yeah. Threshold